I want to thank the organizers for organizing this workshop. This is actually the first time that I'm giving a talk at IPAM, so this is huge for me. My background is in mathematics. I'm in the Department of Mathematics at Northwestern. I'm also part of the National Institute for Theory and Mathematics in Biology in Chicago. So before I forget, I need to tell you that please consider applying to our programs. Come for a short visit. Come to organize a workshop. Sorry, IPAM. But check our website, OK? So I'll go slow. That is sort of my plan. I want to talk about a few open problems in mathematics, OK, related to dimension reduction and energy landscapes. So they can be motivated using biology, and these methods are heavily used in biology. Okay, but I'll focus on the mathematics. Please interrupt if you have questions. So first thing I want to talk about dimension reduction. We've seen a lot of dimension reduction methods in these 3 days. Here are a few examples for single cell transcriptomics. You see UMAP, you see t-SNE. This is sort of like the state of the art. You see these pictures. Okay? As a mathematician, I want to understand what I'm actually looking. Okay? I want to understand these shapes. When do they happen? Why do they happen? Okay? This is sort of like my the first challenge. Okay? And I'll ask like really baby questions. Okay? So I start from dimension reduction. Dimension reduction, if you try to just frame it as a math problem, you can just say, okay, I'm starting with any data points that are denoted by x1 to xn. They live in some high dimensional space, Rd. And our goal is to find a low dimensional collection of points. This is the output, y1 to n, so same number of points, that capture most of the geometry of the initial data set. Okay? Okay, for a mathematician, now we have a problem, except that this is extremely well posed. Right? As a mathematician, I need to define what I mean by capture most of the geometry. And as soon as you even if you do baby examples, you see that this is actually part of the problem, right? If you start with 3 points in dimension 2, a triangle, there is no way to actually just fit the triangle in dimension 1. Okay, you need to make a choice. Okay, and here I'll focus on D will be very large, the input data, and the output will be 2, dimension 2, because I want to visualize. Is that okay? So part of the problem is actually to define what do you mean by capture most of the geometry. And different methods will have different goals, as we saw. Okay. I want to start with just one theorem because I have to give a proof in every talk that I give. It's part of the business. This is one of my favorite theorems, and it's also an example of something that is beautiful but not useful. Okay? And this is Johnson-Lindenstrahl's lemma. It goes back to the 80s, and it says that if you start with any collection of points in dimension D, okay, you take any data set, then you want to find your output, which are called f of x. So x is a point. I'm trying to find f of x, right? In such a way that I'm preserving distances. And I give yourself some room. This is the role of epsilon. Right? You can make mistakes. I'm not asking for an isometry. I mean, I can give you some room. And Johnson-Lindenstrahl actually tell us that it's possible to find such map. This map is even linear, so it's easy to compute, as long as you pay one price, which is the output dimension needs to be lower bounded by some, a priori, perhaps small constant. There's a log there. Okay, this is beautiful. Problem solved. You can go home. Okay. Except that in practice, if you give yourself, let's say that your input has dimension 10,000, and you give yourself like 10% bigger room, then the output needs to be in dimension 250,000. Okay, so extremely not useful. Again, our goal is to have the output in dimension 2. Okay, why do I say this is a gorgeous theorem? Well, this is a gorgeous theorem because you can actually prove during the next break. Okay, and it's a nice example of a deterministic theorem that the method is using probability. Okay, what is the solution? I can actually tell what the solution is, and this is the sketch of the proof. You actually just take your map to be just a random matrix. Just flip coins. Okay, independently of every entry. with high probability this will work. If it doesn't work, you apply it again. Okay? Seriously, this is the proof. Okay, sketch of the proof. But anyway, so this is a starting point for dimension reduction methods. What I want to talk is about t-SNE and UMAP. Okay, but before I get there, here are two data sets that I'll show pictures of. One on the left, this is a Gaussian mixture. This is just a collection of centered, well, half of them are centered in like independent and identically distributed Gaussians in dimension 784. Half of them are centered not at 0, but at some vector E1 times some constant t. Okay, so half of them are shifted. And here is MNIST. Okay, so these are just handwritten digits. Each unit here is 28 by 28 pixels, so dimension 784. That's why I choose this. Okay, and I'll just show you why t-SNE. If you go to the original papers and UMAP, they became like a highlight. It's because they actually work in this data set, while previous methods, they didn't. Okay? For instance, if you, just to show an example, if you try to do Johnson-Lindström, okay, use the map that I show you, just this matrix is just a random matrix. This is evidence how it's poor performance, right? So on the left is your mixture. You should have 2 clusters. On your right is like you should have 10 clusters. It's just a blob. Okay, this is just to show you an example. But I'll go to one method that actually, this will highlight sort of my perspective. This is a method that many of you taught in your class of linear algebra, PCA. It's old. You take your matrix, your data, you construct the covariance matrix. You do X transpose. This is a symmetric matrix. You can diagonalize. You look at the eigenvalues and the eigenvectors. You order them. You take the 2 top the 2 eigenvectors associated with the top 2 eigenvalues, and then you project. Okay. What you see is that actually for the Gaussian mixture case, it does really well. It's split into 2 clusters. In fact, this is the picture that I used to motivate the Gaussian mixture in the previous case, right? But for MNIST, it's still a blob. Okay. And this has been around for a long time. This is a linear method. We understand really well why it works, okay, and when it works. PCA, and we've seen this, if you take, for instance, your data set to be just noise, okay, so I'm taking my X to be just, again, just independently identically distributed random variables. I multiply by its transpose, but then I add a signal, okay? And I add a signal that has that it's of low rank. So here's rank 1. Okay. So if you're dealing with the data set that its signal is low rank, t-SNE actually PCA does really well. It actually captures the feature. It captures the signal, and this is actually a theorem that goes back to BBP. This is called the BBP phase transition. It goes back to Baik, Benahus, and Péchet. The top eigenvector actually localizes, and the top eigenvalue actually just gets away from the bulk. If you just had noise, you see Marchenko-Pastur. We saw this yesterday. As soon as you have noise plus a small rank, here I think the picture I have rank 2. If you have rank K eigenvalues will just pop out of the bulk. Okay? And this is a way to identify the signal. Okay? All right. This was PCA, 100 years old, still very, very useful. There have been methods throughout the years. Nonlinear methods started with Salmon. We've seen isomaps in the previous talk. This is how isomaps performs with the Gaussian mixtures and MNIST. Okay? Isomaps, I'll come back to the construction of isomaps. It started with just constructing the graph of k nearest neighbors, or epsilon neighborhoods. Laplacian eigenmaps, you use the same graph using a data set, but now you build this, you look at the Laplacian, and use the Laplacian to diagonalize the Laplacian, and then you use PCA on that. So you see that this actually does well with Gaussian mixture. That's well with MNIST. But then you get to t-SNE and UMAP, and you start to see these pictures.
Can you just remind us one more time, what did the PCA look like, the top two PCs on those two? I just forgot.
I'll go back. PCA looks like this. OK? Right? PCA, it's like the prototype to get rank 1.
Yeah, of course.
So the Gaussian mixture is like the easy, right? For MNIST, the signal is not low rank, right? It gets bubbles. Okay. And then you get to a t-SNE, which was introduced in 2008 by Van der Martin Hinton, and you start to see these pictures, these clusters. Okay? And then UMAP, 10 years later, you start to see this again, this MNIST.
So you haven't explained to us what UMAP is.
No, I'll explain in a second. Okay? That's my goal is to explain these two. Okay? Or maybe make you more confused. Okay? But anyways, this became the state of the art. Okay? And in single cell business, UMAP and t-SNE are widely used. Okay? So let me explain t-SNE first. Okay? Because once I explain t-SNE, you can actually just define UMAP. It's actually pretty easy. What is t-SNE? Okay, so t-SNE, again, I start with a collection of points in dimension D. This is my input. And what I'm going to do is that I'm going to construct probability measures attached to each of the vectors. Okay, so there will be any probability measures. And the way to see it is that this is like if you're at data point xi, you will have some measure that captures your preference. Okay? You're going to choose your favorite other data point according to some probability. Okay? So that measure I'll denote by mu j. Is that okay? So from the input, I construct a collection of any measures that captures sort of similarities of your data set. And I do the same thing in dimension 2. Okay? For any collection of vectors y1 to yn in dimension 2, I'll also construct a sequence of output measures nu1 to nu-n. Okay? The point is that the measures that your preferences, they are supported on the other data points. Okay? So I'm, in fact, to define nu1, I just need to define n minus 1 numbers that add up to 1. Is that okay? Okay. So in order to define this vector of measures, I just need a matrix Pij, where in each row it adds up to 1. Okay? And now what I'm going to do, I'm going to compare the measure mu I, that's the measure that I created for the input, with the measure nu I, which is the one that I'll just create for the output. How do I compare measures? Well, there's a classical way to compare measures, and this is just one example. You can use KL divergence. Okay? You can compute the entropy between these, how similar they are. And this is actually no negative. It's a quantity that it's 0 only if the measures are the same. And in our case, where we have actually, we can just construct the matrix P and matrix Q for the output. P will be the input. And the matrix has actually a nice formula. It's just a sum of Pij log ratio Pij Qij. Yes?
So when I compute the entropy, I'm not viewing it as a probability measure on RD. I'm viewing it as a probability measure on zero.
Exactly. You're viewing a probability measure on just the index set 1 through n. You already forgot. I didn't tell you how to construct the measures yet. That's part of the business. But now I'm just looking at, I'm comparing the measure mu I with measure nu I.
Because I was confused because in priori the measures mu and nu are on different spaces.
They will be in different space, but now I'm just looking from as just using the labels because I want to map xj to the vector yj. Is that okay? Good question. Yeah, please interrupt me, okay? So now, with this, I need to tell you how to construct these measures, okay? And this is the most technical slide that I have, right? So don't panic. This is the input, what you're going to do, and this is actually the really important part, okay? You're going to use Gaussians, fine. But there is a term that I'll come back. It's how to actually normalize each of these Gaussians, okay? So the normalization for each of these Gaussians will depend on the point, on the data point xi, okay? So if I want to construct the measure mu I related to the point xi, I use its information, And this information will actually be captured, well, first by the distance, but also by this standard deviation that I'll come back to it. Okay? Keep that in mind. I'll come back. Yes?
So is there a reason you chose this radial basis function rather than other Gaussian kernels?
I'll come back to that. At this point, I'm just using this because this is in the original paper. But soon, we'll consider different kernels. Okay? The important thing actually here is one, decay of the kernel. For the input, the important thing here is just to make sure that you have exponential decay. You don't even need Gaussian decay. And second, it's how to scale near each point. So that's the role that this standard deviation is actually playing. Okay? The second point is that for the output measures, I'm not going to use, and this is actually the main idea for t-SNE, and that's the letter T, is that for the output, instead of using Gaussians, you're going to use a heavy tail distribution. You're going to use a T distribution, something that has a heavier tail. Okay? And again, the goal is to minimize the entropy between the sum of these, or the sum of the entropies between these measures. Okay, so we'll try to minimize this functional. Qij will be something, Pij's are given. We'll try to optimize over Qij. Okay, remember X is given, this is constructed. I still have to do how to do this standard deviation. So the P's are given, I need to optimize in Q. Okay, in practice, how do you do it? Well, you start with some random initialization. You can use PCA first. You can use Laplace eigenmaps first to initialize. And then you run a stochastic gradient descent, trying to optimize this function. Am I good? Mm-hmm. Yes?
Is that Pj given I the Pij?
Oh, no, this is just notation that I'm trying to, I is the data point that I'm trying to build the measure. What is the probability that I prefers J?
And
It's not given, it's just notation.
Oh, wait, I saw the Pij.
Got it? And then I just symmetrized. Okay, just to make life easier. Yes?
Is there a good way to understand the advantages of using t-SNE rather than, say, Gaussian SNE, or I think it's just SNE?
Okay, here's my blurb. Okay, putting heavy tails in the output in lower dimensions actually allow us to explore a bigger part of the space. If you try to do Gaussians and Gaussians, this is actually SNE, the original SNE. The performance is not as good. The pictures that generate are more like blob-like. Okay, this is just my blurb.
Is that because of the distortion, the inherent distortion in metrics that happens? When
Exactly.
So you'll never be able to get less than some distortion.
It's again, you're trying to solve a problem, you need to compromise. Okay? Yes?
Following the line of this question, I mean, if what you want is like a heavy tail at the end, and this is the optimal distribution for the heavy tail, the T distribution. So in other words, if you use other heavy tail distribution, would you get like better results or different results? Or?
Okay, I'll reply like this. You have to define better. Meaning that if you put a different kernel here, I'll get results and I'll show you.
Different results, say.
Yeah, I'll get similar results, in fact, but with different taste. Okay? Again, I'll make you more confused.
Maybe.
Yes?
My comment for people is just that you see in that KL divergence formulation, the probability that's multiplying the log on the left, if that is very low, t-SNE effectively has no penalty. So it has basically no penalty for things that are far away. So that heavy tail makes it care a little more about things that are far away, supposedly. But as you've seen me show in my portion of the talk on dimensionality reduction, it's still pretty bad at placing things that are far away.
Thank you, Smita. There you go.
So the optimization will be in an n-dimensional space?
My optimization will be on the Q's, okay? With P's as my variables are given. Okay? Okay, I have a video so that you can see, this is actually t-SNE, this is actually gradient descent. We started with just random initial data, and then I stop at some point, and I'm doing t-SNE, and you see these pictures. Okay, this is actually
Random initial data that has some structure.
the data has structure.
Okay, you didn't like, it's not.
It's not random initial data. It's
It's
actually
not like
this from epithelial
not
cells.
uniformly
This is actually from
random.
epithelial
Okay.
cells. This is actually biology. No.
So how bad is the landscape in terms of?
That's when I go to the board, I'll talk about the landscape. Okay, so that's part 2 of the talk. Okay, but you see, again, you see, even starting with just random initial data, when you do gradient descent, these clusters, they form. Okay? All right. Oh, I'm sorry. Okay. t-SNE, if you go to the paper from Van der Meten and Hinton, 56,000 citations right now. Wide range of use. In mathematics, there are very few compared to the 56,000. Okay, I'm pretty much that this is a comprehensive list. Okay, I apologize if there is a paper that I'm missing, please send to me. But this is the comprehensive list of mathematics in t-SNE. So mathematicians, they sort of like miss the train somehow. Okay. I will make a few comments. The first 2 papers here, they analyze if well-separated clusters, they remain.
With a Zoom question.
Oh, yes, please.
It's so cool. The hand went up.
Wow.
I realized they did that.
Questions?
Yes, on Zoom. Eduardo,
On
I
Zoom.
think you're supposed to let them
On
have
Zoom, the hand went up.
Eduardo, you're.
Oh, I'm supposed to do something?
Yes.
I have no idea what it's supposed to do. Yeah, it doesn't say how to unmute, so I have no idea. This is a black box, literally. Yeah, I'm sorry, I have no idea how to.
His hand came up.
Okay, sorry, now I can unmute. I was just going to say that we did have a mathematical conference on dimensionality reduction at Dogstuhl last year, and we have a very large review coming out, but I'd like to point just to one flavor of paper from Hamprecht Lab, Friedrich Hamprecht in Heidelberg. He has a paper on the repulsion attraction continuum, which I find very interesting. And I
Okay.
just wanted
Smita, send to me.
Yes, I will send to you.
Thank you. So one more line here.
So a very short question. Because this is a question somebody asked before in Smita's talk. So in principle, from what you described, you could do this with projections into 3D or 4D.
Oh, absolutely, absolutely.
There's no reason not to do it.
No. And the terms that I'll show you, the value with any output dimension.
Does
I'm
the-
choosing 2 because I want to visualize.
No, I understand.
I mean, the estimation, the computational runtime is somewhat proportional to that, right? So it does
Absolutely.
get very slow. Just
It gets really slow.
yeah, my experience is that if what you really care about is doing an approximation
Okay.
for high dimensions, not for visualization, you would probably use a different method.
Okay.
Usually.
Oh yeah, that's actually one of the distinctions between diffusion maps and fate, which Smitha was talking about earlier, is that diffusion maps a lot of the time will get you from 10,000 to 15, which is cool for doing stuff but terrible for pictures, and then fate does a bunch of other things to help you get down to like actually having a picture you can look at.
All right, so again, the initial papers were dealing with well-separated clusters. What I want to talk here is about when I did work back in 2023 with Fletcher and now with Gu. This is how I started thinking about t-SNE, and it was a very naive approach. I was just thinking, okay, what happens if I take pure noise and apply t-SNE? I should see a blob. Okay. So when I started to get interested in t-SNE, I was just looking for papers who will tell me the answer. What is the null distribution for t-SNE? And surprisingly enough, there was nothing. Okay. And the next question, which is perhaps the next question after just asking about the null distribution, is that imagine just have noise and I put a signal, just like in PCA. Okay, taking just a low dimensional rank 1 signal, how strong should be the signal so we can actually detect, to actually split into 2 clusters? And can we actually recover? Okay, so that's how I started. And it's easy to simulate. Here's one example, t-SNE started with just pure noise. My noise is Gaussian in dimension, I think 500 here, 100,000 samples. You see the blob. As you expect, you see something that it's rotational invariant, symmetric, except that the density inside, it's not from a uniform distribution in the circle. It's something else. Okay? And I just wanted to understand what is this something else. Okay. And I was taking the approach that the input dimension is fixed. The output dimension will be 2. And I'll send a number of data points to infinity. So I want to see these pictures as the number of points goes to infinity. Do they actually converge? And if they converge, they should converge to a measure, a probability measure in dimension 2 on the plane. Okay.
Sorry, iterations means what? Means the algorithm iterations?
Yes, yes. Because at some point I need to stop.
Yeah, nothing to do with that.
Nothing to do, okay? Because at some point I now come back to the landscape because that's actually an important point. And a point that, okay, now let me go back before I state a theorem and try to look at the perplexity. Okay, so I told you that the way that you normalize the input measures actually play a big role, and they do. The way that you normalize is by choosing, make sure that each of the input measures, the mu i's, they have exactly the same entropy. Okay? This is a way just to make sure that if you, it's really a way to scale. Okay? Perhaps near the 0.7, you have a cluster, but this cluster is slightly more separated than in a little point over here, which everything is really close. And you want to keep the two clusters the same. These are two all-separated clusters, but the distance don't match. This is the role of these sigma i's. Okay? Except that there is a parameter, and this is the parameter that you have to input, which is called the perplexity. Okay, so this is a number that you fit in, you choose, and then you run the algorithm. Is that okay? So the way to normalize and choose the standard deviation is through this equation, which I'll highlight. This is actually a nonlinear equation. Okay, and that's what creates the source of the main issues. Right? So you're putting this solution of this nonlinear equation into the standard deviation of these Gaussians. Okay, so here's our first theorem. The first theorem is actually for the regional t-SNE. And here is a point that I'll stress. I'm taking the data points, number of data points to infinity. That's n. And I'm going to choose perplexity as proportional to the number of data points. Okay? This is my choice. In practice, that's not what people do. Okay? People that use t-SNE, they choose a number between 4 and 40. Okay? I'm scaling perplexity with n. Okay? And then it's proportional to n. This proportionality is rho. And what you can show is that indeed, if you take this, if you think this is just empirical measures of the output, this sequence of empirical measures, they will converge. Okay? They will converge to a measure on R2. And this measure on R2 satisfies a variational problem. Okay? I'm not getting into, if you don't know the details, I can share. But that's the message. The measure actually converges, and you can actually be very explicit what this is. Although this is not super explicit, I'll show in a second. If you take the radii, this function also converges, okay, to some function.
A question?
Go ahead.
You say there's a subsequence that converges?
Yes, you need to go to a
Is it not unique? Or?
It's not unique for many reasons, because you have rotational. I mean, if you rotate, you translate, you're still the same process. So you need to fix it. So you have to go through a subsequence no matter what. Okay? Everything.
Radial distribution is unique?
It is unique. The solution is unique. Can I write anything about it? No. Okay, I'll show you in a second. Okay, what happens if you add a signal? Okay, and by the way, the first paper was essentially for t-SNE. The second paper was just for generic kernels. The assumption of the kernels were, for the input kernel, you need exponential decay. For the output kernel, you need to be alpha stable. Okay, so you need to be heavy tail with some parameter alpha. Okay? For each one of them, that leads to a different variational problem, which may lead to a different measure. Yes?
What is IRO?
I'll write IRO in a second. This is the function that I'll try to optimize. Okay? So this is the variational problem that in the end, the limit satisfies, and I'll show you in a second. Okay? So if you take now the second question, if you take noise plus just a rank 1 perturbation, so this is the Gaussian mixture case, then you start to see this, this is simulation. And what you can show is that actually there is a moment in time, depending on the strength of the signal, there is a strength, such that the support actually disconnects. And apparently, I don't have a proof. If you just focus on one of these blobs, if you send t to infinity, then you recover the measure that I had in the previous slide. Okay. Okay, now answer your question, Charlie. What is IRO? And this is a source of why it's actually difficult to get anything explicit, is that in order to define IRO will be a function of the space of measures. The way that you define this is essentially a Gaussian kernel. But now, what you have to do is you have to actually decide what is the standard deviation that will show up here. And you have to solve this nonlinear equation. So part of it, you have actually to define, to actually prove that for such function, there is a unique solution. I'm going to use this sigma star as an input, and I will define what IRO is. And then IRO is essentially like the entropy. But now where this kernel use the standard deviation given by this implicit solution of the previous slide. Okay, perhaps this is the most technical slide I liked. But again, the point here is that this limiting t-SNE is highly nonlinear, which makes the variational problem actually hard to analyze. But maybe actually we don't need to analyze it. That's another question, okay? I think no one actually did numerical solutions for this. It would be interesting to see how it compares to actually just running t-SNE and actually using these. It's a good point.
To go back to Ruth's question, so different subsequences could do different limits. So this means that there's a group of symmetry in the solution.
Yes, yes. And if you remove the orthogonal transformations, this is unique.
I would say it's only up to orthogonal. Okay.
Okay. Okay. Some open challenges here, and I'll go to how many minutes do I have?
Should have plenty of time. 11:25, but then we have 10 minutes for questions.
Okay. So okay. So and this is the next thing that I want to tell you. When you try to optimize t-SNE or UMAP, you're solving. You're doing a stochastic gradient descent on this entropy functional. This is highly non-convex. Okay? Understanding the landscape itself is a challenge. And again, you're running a stochastic gradient descent, you're deciding to stop. There's no reason why you should stop at the minimum. You could be at a local minimum, near local minimum. In this landscape, it actually has, it's expected to have exponentially many local minima. Okay? Which means that if you run again, you may end up at a different local minimum. Okay?
Have you done that experiment?
What, the experiment of running again?
Yes.
Yeah, the picture is completely different.
So, every time you pick a random starting point, you get a different answer.
Yeah.
And when you say they're exponentially many, exponentially in what?
Exponentially in n, the number of data points. Okay.
This is just picking vectors in R2, essentially.
Yeah. Okay. The theorem that I showed you is actually very soft. I showed the existence of the limit, what should be this limiting t-SNE. In practice, for practitioners, this is essentially, I don't want to sell myself short, but useless. Okay? Because you need quantitative estimates. Okay? In the ideal world, this would be the null distribution. Okay? This would be available to actually just create statistical tests and have p-values when you run t-SNE. And make sure that we have X amount of X clusters. Yeah, go ahead.
Sorry, I just follow up on Shmuel's question. So why is it? I mean, is easy to prove that you only have exponentially many?
No, there's no proof. There's no proof.
Oh, so it could be much bigger than exponential.
It's expected to be exponential, but it could be that it's.
I see. Okay.
There's no proof.
Okay.
It's not obvious. It's not to me.
I have a question.
Go ahead. Sure.
So it's, on the one hand, you had exponential, you have essentially every time you restart the algorithm, you get a different choice of y's. But how about the measure that they construct? How different are the measures, the q's?
It could be they're very close to the ground state.
So, but are they? I mean,
I do not know.
many
I do not
y's
know.
give the same q?
I do not know. Okay? And I'll show you one example when we talk about energy landscapes, if I have time, that if you just take random functions in high dimensions, there are cases where you see this phenomenon of exponentially many critical points. They all orthogonal to each other in space, but their values are actually really close and close to the global minimum. Meaning that you're essentially solving the optimization problem, but the way that you learn is actually very different.
But wait, but when you visualize it, it's going to look completely different.
Yeah, because that's the position. The visualization is the position in space.
Right, and that could be completely.
And you're optimizing the same problem, but that could be completely.
Well, maybe you need to add a penalty term for the y's. If you want to optimize this, you want the y's to be as spread out as possible in the end. So you want to maximize, the sum of the distances between the y's or something like that.
Oh, I'm sorry. What did I do? Anyways, I promised to talk about you. Oh, it's weird. Oh, because that's the last slide. Yeah, I want to move to the board. That's why. The solutions that I show you they're actually noise dependent. If you change the distribution of your noise of your input from Gaussian to something else, that will change the variational problem. I assume that the solution of the variation problem will be different. How different? That's another question. How to choose perplexity? Here, in order to actually have a limit, you have to choose perplexity proportional to the number of data points. That's what people don't do this. Okay, and some of the most recent results show that if you don't do this, things blow up. Okay, you don't see the clusters. So there is something there to be understood. Last, what is UMAP? UMAP is also like the soft UMAP. Okay, so the algorithm UMAP is essentially t-SNE, but at the first stage, what you do, you construct the k nearest neighbor graph. Okay, so you start with the input, you look at the k nearest neighbors points to it, and now the measures will be supported only on those points. So in some way, it's a way to do t-SNE, but your kernel is non-smooth. You just put in an indicator function. An indicator function that actually would depend on scaling. So instead of using perplexity, the k itself would depend on the data points, and that creates a non-smooth version of t-SNE. For UMAP, that list that I showed with 7 papers, well, there are none. Okay, just because of that difficulty. Yes?
Why then? I mean, maybe it's just a marketing strategy, but when they say that UMAP, at least the authors, is something that is preserving topologies, even based on TDA to some extent. t-SNE clearly is not, right? So if you say that is basically t-SNE with some the support of the graph and with some indicator function, how come it's preserved?
Well, the original paper motivates UMAP using fuzzy sets and algebraic topology and category theory. In practice, when you write the algorithm, that's why I say soft UMAP, you actually don't need the whole history, well, the whole story to implement. And in fact, what you're doing is actually just choosing these k nearest neighbors in a way that the k is clever. Okay, the k changes with the data point, which translates, and then essentially you optimize the same loss function. Okay, so the point is that you could translate this choice of k as putting an indicator function of a ball of certain radii at each data point, which essentially means that your kernel went from something smooth, Gaussian, to something Gaussian indicator function. Okay? That's the way that I interpret. But this difficulty actually just, it's serious, this non-smoothness.
But then in the interpretation they are making to claim that the topology is...
I mean, it's a fair way to motivate UMAP.
To motivate, but the algorithm, is it preserving?
No.
No. It's just the motivation, right? It's just marketing.
I'm going to get the tree to the earth.
Oh, the board, yeah, let's go to the board. Okay, okay, how many minutes do I have? Oh, it's done.
Well, we're in the question.
I just wanted to do one more problem, which is, again, if you take UMAP and t-SNE, and you look at the loss function, I'm writing this is L of the QIJs, okay? QIJs became X because I'll look at different loss functions. It is expected that this is highly non-convex. And with exponentially many minima. Okay, and exponentially, and again, my X here for t-SNE and UMAP, this is just the QIJs. So this is an I and J between 1 and n. So this is exponentially in n. Okay, the number of variables, maybe n squared. Okay, I'll give you two more examples where this phenomenon is expected when this phenomenon is actually known. Okay. The first example, so this is this is just expected, okay? No one knows how to show this. The second example.
Exponential in n or in n squared?
It should be n squared. Okay. The second example is a very simple function. You take x1, xn points in the two-dimensional sphere. Okay? And then I'll define a function which is just minus the sum over ij log of xi minus xj. Okay, so those are with potential. Finding the minimizer or maximizer, I always flip. This is Ismail's 7th problem. It's a famous problem in mathematics. Finding the maximizer is difficult. This function is expected to have, once you properly remove the symmetries, exponentially many critical points. Okay?
The fact that L happens, I'm sorry, so when you say L happens to be like that, that's L was a complicated formula, but it simplifies to this and this.
Oh, no, sorry, this may be by L1, this is not the same L, okay? I'm just giving you 3 examples. But this has actually the same flavor as the entropy.
It has nothing to do with it.
But it has nothing to do. I'm just giving 3 examples where things are expected, they're similar, it's the same phenomena. Trying to get an analogy. And this is like an old problem in mathematics. Okay? The third case, and this is the place where I come from, is imagine that you just take a random function in high dimensions. Okay? The sequence function that I have in mind is a polynomial. I'll make it even simpler. I'll just pick a random monomial. Okay? So I'll pick my function to be L3 of x to be the sum of I, j, k, some random coefficients, xi, xj, xk. This is a homogeneous polynomial, degree 3. Is that okay? My point x here would be high dimension. So this is now on the sphere in dimension n. Okay? I claim for this function, almost surely you have exponentially many local minima. And in fact, for this function, these local minima is actually just, if you pick 2 at random, they'll be orthogonal on the sphere. And if you want to go from one local minima to another, you need to climb a barrier which is divergent in n. Okay? This is a theorem. I mean, I'm out of time. What is nice here is that if you take this monomial, this is not special. This is like p equals 3, degree 3. But if you take degree 3 plus a degree 36, so if you change your polynomial, then these barriers could actually just be removed. And now you have exponentially many local minima that you can actually navigate at the bottom. Okay, I'll stop here.
Yeah, and is the value of L3 near the bottom for all these local minima close to each other?
If you do, yes, depending on how close you mean, right? So you can actually tell where the local minimas are. And the large majority of local minima, they're essentially with the same value of the function.
But you said the barriers when you added something.
The barriers are divergent. In this case.
No, but when you added something, they're very small. So something like simulated annealing or something would probably work well.
Yeah. So if you take this function and you add something with degree 38,
right? Then simulated
and suddenly this, yeah.
Wow.
Anyways.
And all the connecting critical points of index 1 are around the same height also?
Yes. For this case, yes. You actually have a layer structure, you can talk.
So you said that UMAP was harder to analyze because it's using a KNN graph rather than a dense graph constructed with a Gaussian kernel. But if I'm remembering correctly, it also uses the Laplacian eigenmaps as like a smart initialization, whereas t-SNE does like random stuff.
You could use Laplacian eigenmaps to t-SNE too. That's a way how you initialize.
But in your theoretical analysis, are you assuming that you're initializing with Laplacian eigenmaps or uniform?
Uniform.
Because what I'm wondering is because you said right now you're able to get convergence without a rate, but there's a whole bunch of results on the rate of convergence for the Laplacian eigenmap. So I was wondering if you make that assumption, if you'd be able to bootstrap that and then get like a quantitative estimate in your theory.
I would not know how to do this, but this is actually a nice idea. Just talk more. Okay? Because I use compactness at some point, so I lose control of quantitative estimates. Yeah.
There's a question back here.
Yes.
Is there any estimate of how those local minima differ from one another? Is there
In which case?
any case? I mean, if
Well, the
they
case
are,
that we know more is this one, and I don't know what you mean by differ from each other. I know that if you pick two local minima in this case, and you want to go from this local minima to the other, then you actually need to climb a barrier, which I can actually even tell you what the size is n times a constant, where n is divergent.
but the values of the local minima,
They're really close.
So maybe you don't need uniqueness.
No, maybe you don't need, maybe the method is efficient. We're all learning the same thing in different ways.
But we don't know that that's true for L1, which is what we're really interested in.
Exactly.
So
Exactly. This is just an analogy. Yeah, this is just an example.
I think there's another question on this side. Did I see a hand raised?
Yeah, so I have a question. So you talked about how if you take a Gaussian distribution, you get some radial distribution, right? So how is that radial distribution related to the earlier distribution? Like, do we know anything about that?
I'll have to think about it.
And also, what happens if I replace Gaussian by heavy tail? Like, say, I take a power.
I do not. Maybe it actually works. It's just in the proof techniques, I use concentration inequalities. So that's why I need exponential tails.
I think Ben has a question.
So how often, if you do different random initializations and you run SGD, do you get to the same local optimum versus different ones?
In which case, for t-SNE?
Any of these three. Like, is there anything known about?
I don't think there is. Okay, I will not. I do not know. Okay, I'll have to. Probably there is nothing known there, but I do not know.
Do you know in practice what people do with initialization when they're running? Is there some standard way people do it? Do they use one?
They use Laplacian eigenmaps first with the data, and then with Laplacian eigenmaps, then they implement UMAP. Or even PCA in the beginning.
I have a sociological question.
Go ahead.
So you see these papers where people use t-SNE or something, and they say, we managed to distinguish the cell types, which we know, this worked great. Has there been some selectivity of which of the solutions? I mean, if I run this a million times, and except for one time I get the wrong classification, and then I just publish the one that worked, have people tried to reproduce these things and see would I get different conclusions?
I think the message here is that t-SNE, UMAP, your favorite dimension reduction method, it's a great detective tool.
But I'm asking a specific
And then you
question.
go back,
Replicate it?
and then you go back, and then you find another experiment that actually justifies your claims. That's my take.
But in terms of finding populations, actually, t-SNE and UMAP are just visualizations, right? So that the way of finding the populations at the end is biological. If you want, you need experiments,
Exactly.
right? But to suggest the hypothesis of a new population, or what you're doing is clustering. So you do the clustering in the latent space, you get the labels for these clusters, and you end up projecting them in a two-dimensional representation, which is t-SNE or UMAP. Whether this representation is more or less, accurate, or I think it's at the end it's more about aesthetics. No, I find something that guides the eyes of the audience or the reader, so therefore I can show that I have these populations for this.
Yeah, but just a comment on this, and I don't know if you saw like Leo Proctor's work on this. I mean, I've been in many talks where biologists show you the UMAP of the t-SNE, and then they start telling you stories about differentiation trajectories.
We actually wrote a paper in Cell Systems 2 years ago, very similar to Leo's paper, showing exactly this kinds of, yes. Anyway, we are actually into the coffee time. Thank you so much.
You're welcome.
This great presentation.
Okay.
And we are back at 11:50.